Okay, feel free to take it away, Walt.
All right, thank you. Thanks, Katie. I'm excited to be here on behalf of the advisory board and the state of Maine. I've been working in Maine for 15 years on floating offshore wind when we first started talking about it with Habib Dagher, probably back in 2008. And of course, this presentation has a lot to do with the technology that has been developed at the University of Maine and also globally and how it's evolved. So I'm going to try to talk about the more generically about the options that the technology that might be suitable for the state of Maine, and get into how do you want to handle questions, and do you want people to wait till the end? Because I don't care.
I think that would work best to wait till the end, unless there's really quick clarifying questions in the middle. Okay,
I think that's right. If we want to stay on time, that's usually the thing that can stump us. So yeah, I'll jump in, and so I put this together. It's a lot of it's stuff. If you've seen some of my previous talks, some of it you might have seen before, but I tried to update most of the stuff so that it's current. Next slide. So the first step here, and I apologize to the people who are already very savvy in wind energy, but I just wanted to set the stage by making sure everybody understood the technology and the technology drivers, which is basically the wind turbine, which sits on top of these floating platforms that will be mounted outside. I mean, in the projects in the Gulf of Maine, but the turbine, which only represents maybe a quarter of the capital cost, is where all the energy gets made, and it's the most prominent feature. The wind direction is important because these machines almost all machines are operating upwind from the tower, so the rotor has to be held upwind, and there's a yaw drive system that does that, and these are all autonomous, so there's with robotics, so the sensors tell the machine how to position itself, and it keeps it there under all conditions. The blades are like the wing of an airplane. They have airfoils, and they operate off of lift and drag, just like an airplane does. But they have a pitch system at the hub that rotates the blades around and controls how much torque the rotor can produce. So when it's in its most benign position, the blades are feathered. We call it feathered, and the blades can't produce torque, so it's just idling, and the wind can come through it. But when there's enough wind, or the right kind of wind, the blades pitch to a power position and then start generating torque. And for these large scale offshore wind turbines, like the one that's drawn in this cartoon here, these machines are about 15 megawatts now, which is a very, very large. And that torque is being transmitted into a direct drive generator, which is that big disc that sits behind the hub. And that generator puts power into a power converter that's behind that inside the nacelle. And that sends AC power down the tower, where it's converted into high voltage power at the substation. And I'm going to get into the different types of that. And there's cables connecting all these turbines that you see in the background into one aggregate wind farm. So the substation is where everything gets aggregated, and then the cable is called the export cable. It's one cable or a series of larger cables that are trenched in the seabed and brought to a land-based substation that's its equivalent on land, where it is joined with the power grid on land. Let's go to the next slide, I guess. So these machines are, this is the actual prototype of the GE 12 megawatt turbine nacelle that was being rolled out back in maybe 2018, 2019. And you can kind of see from perspective the people standing around it, and the prototype blade, which is 107 meters long, that's joined together with 3 other blades to form a rotor that's 220 meters in diameter. And now, since then, GE is still working, selling these machines. They've upgraded them though to 13 megawatts, which is the size of the machine that's being installed at Vineyard Wind. And then they also have a 14 megawatt version. There was some conflicts with intellectual property with Siemens that I won't go into, but GE is replacing this machine with a 15.5 megawatt machine, which they call their workhorse, which is, I think, code for this is the machine that they want to make a lot of these and make these the machines. Vestas has a complement or kind of a machine that's in the same range, 15 megawatts with a 236 meter rotor that they prototyped in 2022. And Siemens has a 14 megawatt machine direct drive that came online in early 2023. Siemens may be working on some larger machines, but one of these machines roughly can supply the power that's equivalent to what is used by over 9,000 households in Maine. And this is a number that's going to change quite a bit as the Maine converts their heating source from oil to heat pumps, which is happening right now. So and then also the electric vehicles will change that as well as people start to charge their cars in their homes. So I just put this down as a benchmark for the year 2020, and I think this is going to change. Next slide. So the key thing for the Gulf of Maine is that the depth matters. The type of substructure that we use will depend on the water depth, and almost everything going in on the eastern seaboard is below 60 meters depth. But we're about to see that change. In California, we know that the depths are closer to between 500 and 1,300 meters deep. In the Gulf of Maine, Maine is fortunate because the depths are really only maybe 200 to 300 meters deep, which is ideal for floating wind. But it does require the buoyant platforms like the structures that are shown on the right side of this. And I'm going to get more into that, but it's most important probably to know that the industry for floating is just getting started. We see that 68,000 megawatts of fixed bottom wind has been installed when we only have about 213 megawatts of floating. The fact that the floating projects are smaller and there hasn't been a lot of them has created a higher cost for the floating systems. And that cost is most certainly going to come down when commercialization starts and we start building a lot more of them, because mass production causes turbines to causes costs to come down because of the learning. And that's true for wind, and it's true for other industries as well. Next slide, please. So this is just the lease area, the wind energy area that we're aware of. This was announced March 15th, just less than a month ago. And this is a larger area than probably what is needed. It's 32 gigawatts if it were built out at 4 megawatts per square kilometer, which is the metric that we're using right now. But if we just look at the state goals and you add Massachusetts to Maine, it's only 13 gigawatts. They probably need more than 13, but less than 32. So this gives BOEM some flexibility to create lease areas that are subsets of this this green area that's shown here. But what's notable, and you probably know this, is that this is probably the furthest from shore wind energy area that BOEM's ever leased. So a lot of the concerns that were raised earlier by the fishermen and have been addressed by just the proximity of this lease area to the coast. And I think we will see, in the next few months, more refinement on where they want to lease. When I did my analysis of this a year ago, ISO New England's planning targets are around 18 gigawatts for the ISO New England region coming from floating offshore wind in the Gulf of Maine. Okay, next slide. These are just some maps that we drew. I just want to point out that on the left side, we've got the wind resource, the average annual wind speeds. These are outstanding, probably the best in the country, in my opinion, for generating power from the wind. On the right side is the bathymetry map, just showing what I already just said, which is basically there's a basin in the Gulf of Maine that you probably know that's fairly flat and shallow, and it allows projects to be built in a very large area relative to some of the other constraints that are in some of the areas south of here and in the West Coast. So a lot of places to put things. Next slide. So this is a chart that Boehm and Bessie drew. It's their timeline for permitting. I just wanted to familiarize people with this before I show the next one, but they're in the process of deciding on where the split is between the Boehm role and the Bessie role, which is the kind of that graduated line that transitions the responsibility of Boehm gradually over to Bessie as the project gets closer to operations. And once operations start, it's the role of Bessie to manage that. But operations doesn't start until you hit that blue bar that's almost further to the right. There's a lot of steps that have to happen along the way, and decision making on the technology happens at stages along this route. And so I just want to, it starts with probably the auction where those technology decisions start to get made, but then there's a long process of site assessment, technology development. There's negotiations that they have to go through for power purchase agreements and environmental reviews until they get to the approval stage. And then there's still a 2 to 3 year period of installation and commissioning. If you flip to the next slide, hopefully that's enough of a familiarization. I added some of these stages to it. So over on the far left, the box at the lower edge indicates about where we are today with the leasing process. We're going through these published leasing notices, and then eventually there'll be a final sale notice that comes out later on this year that leads to an auction. And at that auction is where the developers obtain exclusive site control of the leases that they can purchase. And it's not until that time that they'll start spending money on this, because they have no incentive to do that, and if they think that someone else might get the exclusive control of that site. But once they do, they start putting instruments in the water to measure the wind speed. They start to do geotechnical analysis, and they go through this site assessment plan to do that, which eventually leads to the construction and operating plan, which is further down the line. That might take 2 to 5 years to get to the construction and operating plan. But once they submit that plan, it has a lot of the details of the project, and a lot of the technology decisions have been made at that point. And then if they don't want to have to resubmit that construction operating plan, there's kind of a necessity that they have to stick to a lot of those decisions that get made. But a lot of the details, like say, what's the turbine going to look like, and what exact anchor location will be used, those decisions get made as the construction operating plan is being reviewed, and after that, when they have the FIR and FDR, which is the final design and installation, and the design documents that contain the details of the design, and those get reviewed by Bessie at a later stage. But there's a project design envelope, a representative design envelope that they work toward to get through the COP stage, which doesn't require them to specify the exact dimensions of things, but as long as they stay within that envelope, they're in good shape. And those vary from region to region. But once they get through the approval of the COP, then they can start to build the project. but they can't really build until they get financing, and they can't get financing until they get a power offtake agreement. And those are things that happen in parallel. They can't start building also until the port infrastructure is developed. And so, and that, especially for floating, that's a necessity. So there's still several years away from needing that, but these are details that have to be worked out, because it does affect the characteristics of the technology. So I guess I'll stop there, or keep going there, because I have a lot more to talk about. So this slide shows the three archetypes. You know, these are generalized versions of the types of technology that are available, and I'll walk through each of them separately. But we have the spar technology, the semi-submersible, and the tension leg platform. If you go to the next slide, this is just kind of, before I do that, I'll just want to talk about the parts of the floating wind turbine. I've already done the turbine, so it's the blade and the nacelle are part of the turbine, and the tower is considered part of the turbine too. But then the tower is bolted and mounted to the substructure, which is the part that's the buoyant platform that's floating, and that is moored to the seabed through mooring lines. These are very simple concepts, and then anchors that are the part that attaches to the seabed. And I just for terminology's sake, if we talk about the support structure, it's the aggregate of the substructure, mooring line, and anchor, but the substructure is just the floating part. Okay, next slide. So I started with semi-submersible because that's what most people are talking about doing right now. A semi-submersible achieves its static stability. That means if you put a turbine on top of it, what keeps it from tipping over, just in general, from under normal conditions? And the static stability is achieved by having a wide buoyancy area or water plane area. So you've got these buoyant pontoons or columns that are spread out. These can be 100 meters wide, and the turbine is say 150 meters tall. These are big structures, and that's what basically keeps this from tipping over. So you could literally cut the mooring lines and it wouldn't tip over. It will stay in place, and that's its big advantage. It has a shallow draft, and it can be floated around and assembled at a quayside at a port that isn't that radically different than what we've seen in the past. So, and that allows good access, and it really makes the cost as low as you can get. So we have the most operating experience with these types of systems, but they do have higher exposure to waves because there's more steel at the surface, and they tend to be a little heavier because there's more steel at the surface that has to be held up. And the steel that they're using is thicker and tends to rely on processing plants that might not exist in the United States, and might and for the raw materials as well. And for all systems, I've a flag that we need industrialized mass production in order to make these systems work. I think fixed bottom doesn't really have this as much because these substructures are much more complex for floating. We can mitigate some of this steel concerns with concrete designs, which University of Maine is doing with the Volturnus design. And I think there's several groups that are working on various variants of the concrete application. Let's go to the next slide. And these are just some examples of floating systems that are already out there. The one on the left is the Consortium, is the largest floating. Oh, it was the largest floating project, but now it's been replaced by the Tampen project in Norway. But you can see what they look like from the surface. These are large, probably the largest machines that have been deployed anywhere, or I guess until we had the project in South Fork. Keeps changing, but these machines are 9.5 megawatts and built by Vestas. And on the right is another example of the same technology, really, but a different project called Windfloat Atlantic, which is a 25 megawatt project in Portugal. Next slide. Now I want to just talk about the spar buoy, or the spar. Spar is a long column that goes very deep. It's got a deep draft, and it achieves its static stability through ballast that is poured. Usually it's like gravel or iron ore that's inside the bottom of the spar, but it could be just water that's used, seawater. But the key is to put the center of mass below the center of buoyancy, so that the structure stays upright. The advantage of this system is that it's very simple. As you can see, it's one kind of monolithic structure that goes all the way down, and it's very stable. Again, you could cut the mooring lines and it won't tip over. It's been demonstrated several times in the North Sea, mostly by a company, Equinor, which used to be called Statoil. They've ventured into Maine in the past. But the challenges of this may be obvious. It's got a very deep draft, so you can't build it in a standard port. The draft may be 100 meters deep. And we have to solve that problem before this becomes a commercializable, or a structure that can be commercialized in large scale. In Norway, they can get away with it because they have these deep fjords that are really close to shore. So there are solutions to mitigate this, and the best one, which I like, is the hybrid solution that allows quayside assembly and stability through water plane area at the quayside, but then you can tow it out and then deploy the ballast weight, and it becomes a spar when you get out on station. And Steesdale Offshore Wind has demonstrated this already. And there's other companies like Esteco who actually own the patent on that. And other concepts are that we don't build it upright, we build it kind of laying down. And if we can tilt it down, then we can assemble the turbine and the spar in a shallow port and then tilt it back up. But that requires adaptations of the wind turbines that haven't been approved yet by the OEMs. All right, next slide. And I'll just show you some spar pictures. Spars look more like regular offshore wind turbines because they don't have the substructure on the surface as much. So the Hywind project in Scotland is a good example. There's 5 turbines that 6 megawatts each, which use spar technology, and these are deep draft systems. The TetraSpar on the right side is the Siemens version of that, and that's the deployable spar that they put out once they got out to sea. You can see a little more structure at the surface, but it did the job the way they wanted it to. But it's just a single prototype. Next slide, please. Now I'm going to talk about TLPs, or tension leg platforms. A tension leg platform is quite different. It achieves its static stability by the mooring lines that are connected to it. So if you don't have the mooring lines, it basically is going to tip over unless you do something else. So, but the advantages of a tension leg platform is that it's very stable. It's probably the most stable system that there is, and it has the smallest footprint, and it's lightweight because all of its structure is underwater. It doesn't have to support anything above the water except the turbine itself. So the big challenges, though, is that unstableness during assembly makes it a challenge to install and to assemble. It requires high vertical load moorings, which are not required for some of the other systems. But that's how it achieves such a small footprint, by having those high load vertical moorings. And it does have some dependency on foreign steel, but that can be worked around as well. But the biggest problem right now, I think, is that there's no operating experience in the offshore wind industry. The oil and gas industry has used these several times. I wouldn't say they've got hundreds, but they've got dozens of floating tension leg platforms out there. Again, the mitigation strategies are similar. We hybridize the designs so that they have stable, buoyant systems that will allow them to be assembled and commissioned at quayside, towed out, and then they transition to a submerged platform like you see in the picture. And there's also concrete designs that are using this same approach. So that's the tension leg platform. We like these, but they're probably the riskiest because they haven't been demonstrated yet. But there are some examples. Let me show you a couple. Next slide. This is the SBM TLP that's actually been deployed. They haven't grid connected it yet in France. It's a project that it should be operating this year. And you can see that they have these kind of slanted mooring line, or tendons that go down to high load vertical anchors. And then the system on the right is the Gloston Pellistar that has 5 arms. And the reason they have 5 arms is for redundancy, because if one of these mooring lines or tendons breaks, they still have 4 others, and the machine will still be stable as long as it's not running under high loads. So that's their strategies, and these are both technologies that are being brought forward and are feasible for possible future options for tension leg platforms. There's several others, I just didn't show them on this slide. So there, it's possible, but these technologies, I think, are maybe further in the future because they are still in the stage of needing to be demonstrated. Next slide. So this is just a kind of a snapshot of the market and where the market is. The figure on the left has a dotted line that's representative of today, this year, and you can see that the floating wind market, this is for floating wind, it shows projections of where we think it's going to be in the next 5 years. So this goes out to 2029. So the chart on the left is showing the announced commercial operation dates for projects that are being put through the pipeline globally. And if this is an indication, then we're going to see a huge uptick in floating offshore wind over the next 5 years, starting probably in the year 2026. Of course, some of these announcements might be optimistic because they're based on developers' opinions and what what their targets are set for. The chart on the right, rather, is our projections that are made by industry consultants and experts that are forecasting this development. And these, depending on who you're looking at, sorry, I think that figure's a little grainy, but there's DNV, there's Wood Mackenzie, there's GWEC, that's Global Wind, and BNEF is the kind of orange line, that's Bloomberg. These are all showing their projections based on their corporate intelligence that they collect, showing slightly lower magnitudes for the market in say 2030, upwards of between 10,000 and maybe 2,000 megawatts deployed. So this is just how we're viewing it, and it's important to understand where we're going to be, because learning and industrialization is only going to occur when we have volume production. So we're seeing kind of, if you want to bracket this, somewhere between 14 gigawatts and maybe 5 gigawatts of power by 2030 deployed globally. And I think Gulf of Maine is probably looking at a little bit past that point in terms of when the projects will come online. So let's go to the next slide. This is just a quick view of the cost curve, but I've already mentioned this. The turbine cost, if you're just looking at capital expenses, is less than a quarter of the cost, but it drives the supply chains for everything else on this chart. So if the turbine scale goes up, everything else has to change too, even though the turbine's only 25% of the cost. We have the substructure and the foundation, which is a bigger part of the cost, at least at this point. The electrical infrastructure, the assembly and installation costs, and the soft costs. And this doesn't even include the investments that have to be made to build the infrastructure around it. So it behooves us to build that infrastructure at one scale, and then optimize it as we go. But a lot of the infrastructure hasn't been built yet for these 15 megawatt machines yet, and certainly hasn't been built for the floating industry yet either. Okay, next slide. So now I want to just get into some mooring line discussions. I've kind of hinted at this, but these are just some different types. One of the things that's come into use, traditionally, chain has been the main way of steel chain has been the main way of mooring these systems. And the tendons tend to use steel tubes in the oil and gas industry, but there's a huge transition now toward synthetic rope materials that would be lighter and easier to work with. And there's challenges with them, but we're seeing a lot of this in the different anchor types. But you see that if we're not using the mooring line to support the substructure with its own weight, then we use a lighter weight rope in the areas where it's not touching the bottom. Any place where there's a contact with the seabed, you need to have chain, because the abrasion that happens if it's dragging in the seabed and in the soils will cause the synthetic ropes to fail, whereas the chain is more impervious to that. So we use different methods to anchor them down. If we're using a top mooring system or a catenary, a top mooring system they have lines like the one on the left side that are more at a 45-degree angle, and they don't have contact with the bottom, so synthetic rope works really well. But if it's dragging on the bottom, like the semi-sub is shown with a catenary mooring, where you have to have a lot more chain length, and it has a wider footprint. Let's go to the next slide so I can explain this a little bit better. And maybe just click a couple times to get the pictures to come up on the left side. There you go. So a catenary mooring has the largest footprint, and you can see conceptually it's got it's called catenary because it's the shape that a rope would make if it's just from the shape that it makes from gravity. And so it's really it's supporting the structure because of its own weight, and it takes up a lot more space, but it's very simple, and it can use simple drag embedment anchors like the one shown on the left. But there's a long length of chain that you can see that's horizontally loading that anchor along the seabed. So the trend now is to move toward these other types, either a semi-taut or a taut mooring. The semi-taut mooring still has a large degree of horizontal loading, but we can make it shorter by using less chain and a synthetic rope attached to the substructure, where and that can bring that anchored radius in quite a bit. But even more, that if we use the top mooring, then now we're using vertically loaded anchors for sure. And the angle of that mooring line attaching to the substructure is more like 45 degrees. So we can cut that anchor radius in half by at least by using the taut system. And this is desirable, of course, because now you've got less stuff on the bottom that's crisscrossing around, and there's more space in between the turbines to do certain things that are to do coexistence type things, or continue with the other ocean uses that are out there. Namely, I think fishing is probably the biggest concern. But these are the technology solutions that are being looked at in order to do that. If you use a top mooring system and you change the type of loading that's attached to the substructure, it does introduce engineering challenges that have to be worked out. But so far I'm hearing that those challenges can be worked out, but they do change the design of the structures. And these are decisions that have to be made early on. They can't be, I don't think they can be made after a lot of the design documentation has already been submitted, because they have to pretty much know what they want to deploy in terms of these mooring systems. And that may be one of the big decisions that has to happen under the water. Next slide. This is just some pictures of there's Marco in front of a big mooring rope that we were looking at in Houston one time. And these are just some scale drawings to show the scale of the chain and the rope relative to a 6-foot human. And that's, yeah, just to leave that for a second to have you look at it. These are big, heavy pieces of chain if we're using them. And the ropes tend to be more neutrally buoyant. Okay, next slide. So one of the big concerns is if you got a substructure that's floating in the ocean and the mooring lines aren't tight, like a catenary, for example, or even a semi-taut, or even every structure has some movement, and that the degree of that movement and how far it moves is called the watch circle. That's the circle that's allowed to move within, and it's a design condition that has to be determined on for each type of station keeping system that there is. Now, a big part of that, they're not drifting that far because they really can't. There's the biggest thing is that they've got this array cable that attaches to each turbine that transmits the power over to the substation, and that's a dynamic cable. And if the turbine drifts too far, you will damage that cable either by fatiguing it or actually pulling it out of its connection. So that watch circle has to be controlled, and it's a specification that the turbine manufacturer has to be aware of it in order to make sure that the electrical system that stays intact through the whole thing. So these limits aren't established. I don't have that data with me right now, but these are things that we can calculate, and it has to be designed as a whole system. So, and you can see why. So next slide, please. Yeah, I just did this quick analysis because I wanted to juxtapose and compare the Gulf of Maine to the other lease areas in California, because I think it's important to understand that, you know, after we get past 60 meters, we are floating, but there's floating and then there's floating, if you will. So the Gulf of Maine is shown at the depths that there are, and this figure is meant to show that as the water depth increases, we're going to see watch circles increase and anchor circles increase as the water depth gets higher, but it's going to be different for different mooring types. And so, but regardless of the mooring type, you're going to have some increase. The TLP is going to be the best in terms of not affecting the anchor circle or the watch circle. Top moorings are the next best, then semi-taut, and then catenary. And you can see in the Gulf of Maine, these problems are a lot smaller than they are in the California lease areas that have much greater depths. And that's very simple, maybe oversimplified. I apologize for people who are more savvy on this and understand this, but I just wanted to show that relationship because they're also talking about ultra deep right now, which means possibly up to 3,000 meters. And that's another animal altogether. So on the right side, I just wanted to point out that this the anchor circle diameter does affect the amount of leasable area for a given lease area. And this is just an example of the Humboldt lease areas in California. On the on the left side of that figure with the shapes that show the turbines, the blue line is the actual usable area. The red line is the actual lease area. And you can see you lose about 28% of that lease area in this example if you go to catenary moorings in the Humboldt lease area. So that means you need more area just to support the anchors. You're not making any more energy. You just have to have more area because you can't put an anchor outside of the lease area. And that's what this is meant to show. And in the Gulf of Maine, I don't think we're going to have that as much of a problem like that, and nothing close to the 28%, but it will affect the outer margins of the lease areas and how much available lease area there is. So that's just something to be aware of. Next slide. This is a picture, just, kind of a really cartoon sketch of how the export cables and array cables interact with each other. So the turbines are the dots on this figure, and they are all connected on a string of cables. And each of those strings is attached to the substation that's offshore, presumably in the lease area where the turbines are as well. And so there's multiple turbines, and then as those cables that are on the strings connect, say there's 60 turbines, there's going to be less than 60 cables, but it's going to be a substantial amount still that brings those distribution cables, distribution voltages onto the substation platform, and then increases the voltage on the substation platform, and then an export cable or a set of export cables will be brought to the onshore substation. That could be 40 miles, it could be 50 miles, it could be 60 miles, depending on where the points of interconnection are. And that's how the power is brought to shore. Let's go to the next slide. This brings up, well, what does that substation really look like? This is a picture of the Vineyard Wind substation that was just put in, this year. But it's a fixed bottom substation mounted to the bottom of the ocean, and maybe, I don't know the depth, but it might be about 40 meters of water. And it's AC power, basically, that's being generated at 66 kilovolts in the array and stepped up to 220 kilovolts for the export power to shore. That's the conventional way of doing it. In the Gulf of Maine, because the water is deeper, we're either going to need floating substations or fixed bottom support structures that are a lot longer than what's been done in the past. Now, that either way might be possible, we don't know yet, but the oil and gas industry has built fixed bottom substructures in water depths a lot deeper than the Gulf of Maine. It's going to be a question of economics, maybe environmental impacts. But either one of those is possible. There's a lot of talk and development right now going on in Europe for floating substations. These substations could be done at scale and connected with these high voltage dynamic cables, or there's concepts that are being looked at for bottom mounted substations. But as the export cable distances get greater than 50 miles, there's also a trend toward using high voltage DC systems to reduce costs and also to aggregate power so there's less cables coming to shore. So an HVDC system can carry up to 2 gigawatts with current technology. That's more than one wind farm. That could be 2 or 3 wind farms. And that would have the benefit of having much fewer cables to shore. Let's go to the next slide. I have a few pictures of things. So these are concept drawings of possible solutions to substations in deep water. We have a floating concept on the left side that was that was from Semco Maritime, and that's something that they're looking at with a station that's being held up by a semi-submersible substructure. On the right side, we have a concept for a bottom-mounted substation that's being developed by Acro Solutions. This is something that's been done in the oil and gas industry. It gets the substation out of sight, out of mind, maybe. It's a lot lighter because you don't need the support structure to hold it up. And we have to demonstrate reliability, but they are building some of these now to be tested. And that may be the best solution. We don't know. But these are possibilities that are being discussed right now. Next slide. Now on the question of high voltage direct current, it's the reason to do this is because it's just cheaper to bring, there's a lot fewer power losses on a DC line than there is on an AC line. And there's a lot of reasons that I won't go into on that, but the DC costs just don't go up as much as you get further from shore. And the break-even point is somewhere around 50 miles from shore. On the Gulf of Maine, because the wind energy areas are likely to be further from shore, as we've seen from the wind energy area map, there's a good chance that we're going to be looking at high voltage DC converter stations like the one shown on the left side. And these are very common. There's over 200 HVDC converter stations for land-based, but we're just getting into offshore applications and floating applications, which will be, I think, an adaptation and a challenge, but not a difficult adaptation, I don't think, as we move this into more of the mainstream. But this type of technology also allows backbones and things like that to be for the power to be wheeled into different regions. So I will go to the next slide now.
Hey, well, I just wanted to give a time check. How many more slides do you have?
I was looking at the slide count. I don't think there's that many, but I think that your slides got added to my count. So I'm not, I think I'll try to go faster now if you want.
We just want to make sure we have time for questions.
Yeah. So I just wanted to talk about the above the water turbine spacing here. Typical spacing is based on rotor diameters, not by turbine size, not by any measured distance between towers. So as turbines get bigger, the spacing gets bigger too, because there's just so much kinetic energy that's flowing into the wind farm. And so the turbines get further apart as they get bigger. So a larger turbine doesn't necessarily make more energy for a given lease area. It just makes more energy per turbine. But there's fewer turbine positions, and we like that because fewer turbine positions means less other equipment and more space between the turbines. But there's a big trade-off there that in the maturity of the supply chain and how much you have to invest in building it. But turbine spacing is independent of anchor spread. So the anchor circles aren't going to be affected by the decisions that a developer makes to space these turbines apart. Obviously, the closer the turbines are together, the more turbines you can fit in a particular lease area. And these are decisions that are getting made. They're in the COP and they're specified in the COP, but I think they can be adjusted as they go on. And a lot of the capacity density decisions are being made, not just by the developers, but by the states that are asking, or the utilities that are asking them for power contracts. So that's a big factor. How about next slide? This is just a slide, and I don't want to go into the details on this. It's just that without a port, this is about the floating ports. All the work gets done at the port, a lot more at least than for the fixed bottom system. So the port is the central location where all this is accomplished. You need a deep draft to assemble the systems. You need a lot of storage area. You need a big heavy lift crane to be able to pick that turbine up that weighs like 1,000 tons onto the top of a tower that's about 150 meters tall, and then commission it there at the quayside. They don't do that for the fixed bottom machines. They do that stuff out at sea, which is a lot more expensive, by the way. But so you need a big port to do all this work in, and probably multiple ports, because it doesn't really make sense to take up port space for the marshaling, the installation, assembly of the turbines, to do the fabrication of the components, including the substructures. So we'll probably need multiple ports. That's all I'll say about that. This is a rendering of the Salem port above. And I think this is Salem, Massachusetts is building this port already, but it's just not big enough for floating because there isn't enough acreage. Sorry for giving you whiplash on the clicker, but I'll go to the last slide there. I think that's this is my last before I wrap up. I get questions about this all the time. That people say, oh, wind turbines don't make enough energy to pay for the energy that it takes to make them. And that's just simply not true. This is a chart that shows the life cycle carbon emissions by technology type for different technologies that are out there. The only technology that beats us in this is nuclear. And that's kind of debatable because I don't think they count every part of the supply chain and the waste storage and things like that. But there's but you can see that wind power, and this is for wind power, but offshore wind is similar. It's going to pay back the energy that it took to make it, assuming that the energy was fossils, and it's not going to be. It's going to be from renewables as well, in about 6 months. And these machines last 25 to 30 years now. Empirically, that's what we're finding. So I'll make that my last slide. And I just want to wrap up. We know the Gulf of Maine is going to use floating platforms. That's kind of a given. 80% of the world's resources are floating, though, and this industry is just getting started. So there'll be a big industry emerging. It'll build big supply chains, and that's going to bring costs down. We're going to see this industry become commercial around 2026, 2027, based on global projections that I showed you. The mooring systems with smaller footprints are under development. We want to make those work so that we can maximize the coexistence with the fishing industry and other industries as well. There's probably other co-use that could be done out there. The floating or the bottom mounted substations will likely be used in the Gulf of Maine, and these are technologies that are being developed and evolved in the European markets, and we'll see those be proven before we finish, before we get started, I think, in the Gulf of Maine, actually. And then I think the last slide was just about the life cycle, and wind energy is among the lowest carbon emitters of all the life cycle, of all the energy sources in terms of total life cycle carbon emissions. And that is my my last slide, and I'll just take questions now, I guess, Katie.
Okay, thank you so much, Walt. So